Hi, my name is Zach J, and I'm a tutor here at Chegg.com/tutors. And today we're going to be talking about Raoult's Law, or the law of partial pressures. Basically, what Raoult's Law says is that the total vapor pressure of a solution will be equal to the mole fraction of each solute that is volatile in the solution times the vapor pressure of its pure substance. Okay, so if we only had, let's say, methane here, the pressure of the solution would be equal to the mole fraction of methane, which would be 1 because it's the only thing we have, and then times the vapor pressure of the pure substance. So the vapor pressure of the pure substance is equal to the pressure of the solution because it's pure, and so that would be the vapor pressure of that. Now let's say we have methane and hydrogen gas. Well, we would do this, the total pressure of the solution, the vapor pressure, would be equal to the mole fraction times the vapor pressure of pure methane plus the mole fraction times the vapor pressure of pure hydrogen gas. And in this case, the mole fractions would both be less than 1 because the mole fractions add up to 1. In this case, our vapor pressure would be different from what we would have with a pure substance. Typically, it would be less than what we have with a pure substance. And the reason for that is that, let's say we have this, here's our water interface, and down here we have both our methane and our hydrogen gas, H2, and methane is CH4, right? Well, while they're in this solution, both of them want to go up into gas, and then they fall back down into this liquid phase. They're kind of in this equilibrium between gas and liquid. So we have a gas-liquid kind of equilibrium, okay? So they're both coming up and going back down. And so because these gases are going up into this vapor or this gas form, that creates a gas pressure. And based upon how much of it is being dissolved, it becomes your vapor pressure. So when we only have one gas here, so let's say we only have methane here, all of the methane is here at the interface, and all of that is going to be able to dissolve and go back into liquid, or go into gas and then come back down to liquid, and that's going to create the vapor pressure. However, when we have hydrogens here, or hydrogen gas here too, that is going to take up part of the space here at this interface. So only a fraction of the hydrogen gas can actually go up here and create a vapor pressure, and only a fraction of the methane gas can go up and create a vapor pressure. Okay, and so that's why the vapor pressure, the vapor pressure of the whole solution is a mix of the vapor pressures of these two different components. Okay. Excuse me. So Raoult's law really isn't too complicated. It's pretty straightforward, but some of the problems can get kind of tricky. So I'm going to work out a problem here that is kind of tricky, not as tricky as could be, but it's still kind of difficult. Okay. So basically in this problem we have a non-volatile compound X. So it's not going to be, because it's non-volatile, where it's not going to be contributing to the total vapor pressure. If I wanted to make this problem more difficult, I would say it is a volatile compound with a certain vapor pressure, and that would definitely make this problem a little more difficult. But to keep it more simple, we're going to say it's a non-volatile compound. The solution contains 5 grams of this compound dissolved in 50 grams of water, and the total vapor pressure of the system is 754.5 millimeters of mercury. And the vapor pressure of water is 760 millimeters of mercury. That's the vapor pressure of pure water. And it wants us to calculate the molar mass of the compound that is dissolved. Okay? So from Raoult's law, we know that the pressure of the solution is equal to the pressure of the solvent. So that would be the 760 millimeters of mercury, and multiplied by the mole fraction of the solvent. Okay, because the solvent, the water in this case, is the only volatile substance we have in this reaction. Okay, so from the problem here, we know that our P solution, or our pressure from the solution, is 754 0.5 millimeters of mercury, and that is equal to the pressure of the solvent, which is 760 millimeters of mercury, and times the mole fraction of the solvent, which we don't know at this point because the water is mixed with so much of this compound X, and we don't know the mole fraction. That's what we're going to end up solving for, okay? So doing the math here and solving for how much of the mole fraction is, we find that our mole fraction of solvent is equal to 0.9927, okay? So now that we know the mole fraction of the solvent, we know that mole fraction of the solvent is equal to the moles of H2O, or the solvent, divided by the moles of H2O plus the moles of substance X. So this is just the fraction of moles of H2O. So that's moles of H2O divided by total number of moles. Okay. So what we're going to do now is basically just solve this problem for moles of X because we know our mole fraction of the solvent, which is this number, and we know how many moles of H2O we have because we have 50 grams of water. Okay. And so first things we have to do is calculate the moles of water from grams. So we know that 50 grams of water, and we know that the molecular weight of water is 18.015 grams per mole, and we do that division, and we end up with 2.775 mole of H2O. Okay, so now I'm going to plug this number into this and solve for X. So mole fraction of solvent is 0.9927 from right here. That is equal to the moles of H2O, which is 2.775, divided by the moles of H2O, which is also 2.775, plus the moles of X, which is what we are solving for. Okay, so now I'll multiply this number here by the 0.9927 and distribute that to both terms, and then subtract. Let's just go ahead and do that. So that will give me this here, 2.755 plus 0.9927. I'm just going to call this X for the moles of X, and that is going to equal 2.775. I then subtract the 2.755 from the 2.775, and that will give me that 0.9927x is equal to that subtraction is a very small number. I have to do that really quickly. 0.02. Yeah. Okay. And so now to solve for x, I just divide the 0.02 by the 0.9927, and x comes out to be 0.0201 moles. Okay. So now I have the amount of moles of X, and it just wants us to solve for the molar mass. We know molar mass, abbreviated MM, is equal to grams per mole. And so I will take the number of grams that we had of X to start with, which is 5 grams. So 5 grams X, and then I will divide that by the moles of X, so 0.0201 moles X, and that will give me a final answer of 248 grams per mole of X. Okay, so really not too bad of a problem. Like I said, it can get a lot more complicated if you have more than one volatile substance in the solution, but that really is just right here with the P solution. All I'll do is add, an extra term here that is plus pressure of solvent 2 plus mole fraction of solvent 2. And then I'll do the same thing and solve for whatever needs to be solved. really not too bad if you think about it at the end. Okay, so if you have any questions about Raoults Law, please reach out to me at chegg.com/tutors or any of the other tutors there, and we'd be happy to help you work through any of these type of problems. My name is Zach J, and until next time, I hope you have a great rest of your day. Bye-bye.